Look at this next example. So you can see here we've got some value a, some x equal to a down here, and we want to know if the limit exists when x is equal to a. Notice first of all that if we start from below, so say we start over here from below, or from the left, looking at the diagram, as x gets larger, and we're moving to the right, x is getting larger, the limit is approaching b. So from the left, the limit as x approaches a from the left, I put that little minus sign, f of x is going to be equal to b. All right. What about from the right? From the right, so say we're now starting over here, and x is becoming smaller as it gets closer to a. And we're walking along this curve here, and in the limit, as x is getting closer and closer to a from above, f of x is getting closer and closer to a. But as you can see, there's quite a big distance between a and b. And so at point a, we say the limit does not exist. Where you end up depends on where you start. Right? If you're starting from above a and x is then decreasing, you're going to end up on a different location than if you started from below a and x is increasing. And so where you end up depends on where you start. And we say here that the limit does not exist. And why? Why does the limit not exist? Because the left and right one-sided limit do not agree. Now, remember our very first example. We already numerically showed that the limit exists, and that when x is equal to 0, the limit is going to be equal to 1. Now, a sufficient and necessary condition for a limit to exist is very simply that the limit from the left is equal to the limit from the right, and both these limits exist. And what do I mean by exist? I mean i.e. are equal to a real number, not infinity or an undefined value. And so if we want to show that the limit exists, we want to show that the limit from the left is equal to the limit from the right. And if they don't, then the limit itself cannot exist. Here's our numeric example that we used to show that this function had a limit when x was equal to 0. Notice that over here, this is the limit of f of x equal to ex minus 1 over x when x approaches 0 from below. Notice I got the little 0 there. That's from below or from the left. And this is equal to 1. And then same on the right. So if we're going from right to left, we've got the limit as x equals 0, f of x ex minus 1 minus x. And I want to make sure that I've got this little sign, this little plus, that tells me I'm referring to the limit from above or from the right. Take a look at the problems in front of you. We're going to do some limit exercises together, and we're going to look at the infinity property. And so this is the first time we've done something like this, and it's kind of neat, and it's a good way for you to think, and it has some useful applications in statistics and econometrics. Now look at the first problem. We've got this function, and we want to evaluate x, or I should say we want to evaluate the function as x goes to negative infinity. So how are we going to do that? Well, there's sort of a little recipe that we can follow. Now, normally we would plug infinity into the expression right away. But if you do that, you'll see it's kind of hard to interpret. So why don't we do this? I'll rewrite our first expression like so. And then I'll take advantage of the rules of limits, and I'm going to divide the numerator and the denominator by the highest power in the denominator. So I'm going to divide the numerator and the denominator by x squared. And when I do that, I'm going to get 4x cubed over x squared minus 1 over x squared divided by negative 4x squared over x squared minus 7 over x squared. So I've divided the numerator and denominator by the highest ordered power in the denominator. Now I'm going to simplify it a little bit. So I'm going to keep my limit, and then I'm going to write 4x minus 1 over x squared, and that whole thing divided by negative 4 minus 7 over x squared, like that. Now remember that infinity is not an actual number, but it represents a very large, very big number. So in that sense, if we have 1 over infinity, that's approximately equal to 0. Also, if we have infinity squared, something like that, well, that's just a big number. Big number squared is equal to a big number squared. So we don't need to worry about square terms or multiplying infinity. Infinity multiplied by infinity is just infinity. And this one in particular is going to be important. So those are the two that we need. Now I'm going to go back to our problem here, and I'm going to bring it down here so I've got some room to work. And just like we would with any limit, I'm going to sort of plug in this negative infinity wherever there's an x. So taking the limit of this thing, I get 4 negative infinity minus 1 over negative infinity squared divided by negative 4 minus 7 divided by negative infinity squared, like so. So I've got a really big number multiplied by 4. That's just infinity, right? And then 1 divided by negative infinity squared. Well, that's a 1 divided by a really big number. We'll just call that 0. It's very close to 0. In the denominator, the negative 4 remains, and it's minus 7 divided by negative infinity squared. That's just 7 divided by a really, really big number, and that's going to be approximately equal to 0. And so we're left with negative infinity over negative 4, which is just equal to infinity. So the negatives sort of cancel each other out. 2 negatives make a positive. We don't care. A really big number divided by 4 is still a really big number. And so the limit of this expression is infinity. Let's try another problem. So again, we're going to take the limit as x approaches negative infinity. It could be positive infinity, it doesn't always have to be negative. And we're going to start by taking this expression and dividing the numerator and denominator by the highest order x variable in the denominator. So in this case, it's going to be x cubed. And so we're going to divide the numerator and denominator by x cubed. I've got 5x squared over x cubed minus 3 over x cubed divided by negative 2 over x cubed minus 8. X cubed over x cubed. Now I'm going to simplify. And I get 5 over x minus 3 over x cubed divided by negative 2 over x cubed minus 8. And now I'll take the limit. I'm going to plug in negative infinity wherever I see an x. And so I've got 5 divided by negative infinity minus 3 over negative infinity cubed divided by negative 2 over negative infinity cubed. Just let me fix that up, make sure I can read it, and minus 8. Well, looking at the terms one at a time, we've got 0. Doesn't matter if 0's got a positive or negative in front of it, 0 is 0. Minus 3 divided by a large negative number cubed. That's just going to approach 0 as well. Doesn't matter what the sign is. Negative 2 divided by the negative infinity cubed. Again, that's just going to be 0. And we're left with a minus 8. So now we've got 0 over negative 8, and that's just equal to 0. And so the limit of this expression as x goes to negative infinity is going to be 0. Here's a problem for you to try. Press pause, work through the problem. When you're ready, press play, and then we'll work through it together. Now, remember that the first step is to divide the numerator and denominator by the highest order x term in the denominator. And so that's our x squared here. So we're going to divide the numerator and the denominator by x squared. So I've got x approaching infinity. F of x is equal to negative 3x squared divided by x squared minus 1 divided by x squared divided by 9 times x squared, 9x squared divided by x squared, I should say, minus 5x divided by x squared. Now, I'll do some simplifying. And we've got negative 3 minus 1 divided by x squared, no change there, divided by 9 minus 5 divided by x. So we simplified it as much as possible. Now we're ready to sub in infinity and actually take the limit of this thing with respect to as x approaches infinity. We've got minus 3 minus 1 over infinity squared divided by 9 minus 5 divided by infinity. What's that going to be equal to? We've got negative 3 minus 0 divided by 9 minus 0. We're left with negative 3 over 9, which is equal to negative 1/3. So the limit of this expression as x approaches infinity is equal to negative 1/3.